exactly how I said.
That's what I thought you said. Like,
That's how words fly.
you might think that, but like I literally plan my days out in minutes. So like I have no free time.
Alright.
Say my name. I love you too, Stan. It's a nice to hear you pop out. So you guys, check this out. I know I'm not being very clear with my picture. I've got a region bounded by this sphere and this hyperboloid two sheets.
One sheet.
Okay, well, one sheet of the hyperboloid two sheets. And I assume I'm trying to find volume. I didn't read the question. Yes, I'm trying to find the volume of the solid. And I assume that they want me to use triple integrals.
Yeah.
So using triple integrals, you guys, what section is this? Okay, so this is the section on cylindrical and spherical coordinates. So let's just answer the question directly. I think as a triple integral, the volume is going to be computed on a triple integral over some region E. And the function of the Lagrange position is which one, the first or second? Neither. I think the Lagrange position is just one. However, if I dive in and integrate with respect to x first, so let's talk about how x changes. To do this, I'm going to pull my nifty little red pen. And I'm going to talk about the arrows going from left to, I misspoke, from back to forward that's parallel to the x-axis. And I think the extreme values on that arrow, like at the tip and the initial point, are too complicated. And I don't want to do it. Because you guys have to split up into two different integrals. Because I think the initial and terminal points change whether above or below the intersection of those two surfaces. I think it'd be much more wise to integrate with respect to z first, because now no matter where those arrows are inside that region E in three-dimensional space, the initial points and terminal points are on the same surface. All right, I'll change my game. I guess I'll rewrite this as a dz dy dx. Now I think the z values change from, I said, that means something. You guys, the square root of x squared. Oh, how nice. And the upper bounds are going to be, is it minus?
Yeah.
And I think to find the bounds for y, if you solve in this equation for the variable y, you get.
Give us a second.
Yeah, I will. I'll give you a second.
We haven't even written down the problem yet.
Square root of 9 minus x.
The square root of, the square root of,
9.
I can't hear you.
9.
Yeah, why am I doing this? I don't think I want to solve for y up here. I think to find the bounds for y, what I should do is take a flashlight up and high on the z-axis, flash down and see what the corresponding image looks like in the xy coordinate plane, and see what the arrows do down there in the, I forget, in the y direction. So if I project the image of the solid in 3 space down to the xy coordinate plane, sorry you guys, did I not label that carefully? I said y x coordinate plane. Then I think to find out how the y values change, I'm just simply going to draw my arrows in the y direction. I'll talk about their initial and terminal points. Oh no, I can't. Because I don't know what that looks like. Well, certainly looks like a circle, I just don't know what the radius is yet.
Well, the z part's just going to be 0, and isn't the highest value of the y just going to be when x is equaling 0? So we go, does what I'm saying make any sense?
I'm nervous because if I allow z to be 0, I get a circle whose radius is root 19. Or if I allow z to be 0 down here, gosh, I don't know what I get down there. Actually, I get nothing. Third of course.
I did this really fast, but so you set the z's equal to each other, and then
Nice. I agree.
and then you get 3, and then for x you also get, or from -3 to 3, and then x you get -3.
Now, I agree with that tactic. Because this particular curve, which by the way is projected down here to get the red image, the curve of intersection is what I want to project down to the xy coordinate plane. Let's find it by setting z's equal to each other. Oh, sorry, that's too difficult. Can I change it? I'll set z squareds equal to each other. It means the same thing. And setting z squares equal to each other, you guys, I don't have my glasses on, so help me. Is it 19 minus x squared minus y squared being equal to...
1 plus x squared.
Got it, thank you. 1 plus x squared plus y squared. Or shall we say x squared plus y squared is equal to, I don't know, is that a 9? Oh, shoot, that's just a circle's radius is 3. Actually, I don't even know that over here, but bottom line is that the lower bound of integration for y is gonna be Negative.
9 minus x squared.
square root of 9 minus x squared.
Positive square root of 9 minus x squared.
When somebody said aloud 0 down here, that'd be fine if you're converting to polar coordinates. Sorry, we're triple integrals. Instead of polar coordinates, I meant cylindrical coordinates. And finally, I get the square root of 9 minus, is it y squared or x squared? Yeah, nothing. I think for that outer integral, all I do is look at extreme values of x, constants. And I think x constantly ranges within that circle from one extreme of to very nice. Of course, in cylindrical coordinates, that would go from 0 to 2 pi. Awesome. Caleb, may I ask you a question?
I actually got this far. I didn't know what to do with the.
Oh,
first
my
integral.
apologies. So what do you do next?
Yeah, with dz. Or dy, I guess, after dz.
That's really ugly.
What did the book say? Did it say just to set up or?
Yeah, I'm kind of wondering now that you mentioned that, Caleb. I'm sorry.
The book changed it to actually just after.
Well, you could do use of.
They changed it to
You could do use of.
Okay, so Caleb, here's what the author did apparently. Because he's not discussing the coordinates yet. He said, integrate with respect to z, it's a piece of cake. You get this piece minus this piece in the integrating position. But now you're down to just a double integral. And then he said, like I'm suggesting, now just convert to polar coordinates. Does that make sense? Because that makes me realize so much easier. Because you're right. When I did it in my head, I'm thinking I'm stuck.
Yeah, and then
There's some kind of sophisticated tricks up here. But polar coordinates are good.
I used that online calculator and they did like 7 consecutive subs. Seriously?
Did they really?
Yeah.
Shoot.
What's the are you talking about like it was like Wolfram or something?
Oh, okay. I thought you couldn't see
Wolfram.
steps with Wolfram.
I don't know. It was like a million names.
Oh, you guys, hold up. What I want to discuss today, because we have a quiz,
2 problems, right?
I'm just going to give you 2 examples. So can I just talk some theory first? I think it was really slick when you guys finished your Math 30 course. You got introduced to a nice.
What's the title? What's the important title? What does
Gotcha.
it say?
I don't know what the title is.
Variables and multiple integrals.
Say it again.
Variables and multiple integrals.
Oh, is that what he calls it?
What are you calling it?
Transformations in R3.
And then he says definition to Jacobian transformation.
No, back. Go back. What else did he call it? He called it change of variables. Got it. Or you can refer to this topic as Jacobians. So I guess I got 3 alternative titles. I'm sorry, I don't really look at the book carefully. But you guys, I don't want to just start on the board, right, giving you examples of how to do this. I want you to see a line. So can I just talk for just a few minutes, a little bit of the theory behind this? And I think it was kind of slick how when you guys finish your typical math, Calculus 1 course, Math 30 here at Sierra College, it's kind of slick how you get introduced to a sophisticated topic of integration. I'm referring to specifically, I'm so tired, I'm sorry, U-subs. And I think with U-subs, it's kind of interesting that, for example, this one. Makes your life a lot easier, doesn't it? Do you guys agree? Because that's what U-subs are all about.
Well, you'd have a 1/2
One half where?
on the outside of the integral, or
It doesn't matter. It doesn't matter.
No, it does matter. That's the whole point of this lecture. Oh, so I guess I'm wrong. I'll fix my mistake. Because I think du is related this way to dx. So I think I've got in here a 1/2 du. Do you guys agree?
Yeah.
But notice how with this transformation, how I scale on the horizontal x-axis is different than how I scale on the only u-axis. It's a different scaling system. It's a transformation. It's a change of variables in that sense. And so I think I've got to really worry about what this number, or even expression, might be a variable expression, really is with my particular u sub. Or in today's discussion, our transformation in our grade. So how many of you are currently, I know the answer, but how many have already taken Math 33? It's just 1, 2, 3 of us. And there's a few of us who are in Math 33 right now. So for all of you, you've already seen how we have certain types of transformations in R3 called matrix transformations, where you can commit to some scale changes, some linear stretches, and so forth. Just with matrices, very straightforward stuff. I'm just going to be a little more sophisticated here. So allow me to play for a minute. If I had a U-axis and a V-axis, and I had some kind of region, call it S. And you guys allow it to be a rectangular region, even though I can't draw. Or maybe I've got an initial point right here. How about U sub naught comma V sub naught? That basically means the equations, mine is going to be, I just see if you're here with your Math D skills, it's going to be, you know, Math D is a prerequisite for this course, and many others before this one.
We had to write it down first. You're getting ahead of us.
Sometimes I wonder if you just write it, slow me down.
I write slow. I'm sorry. Now, what was your question?
I can hear you. Is it Y? V equals V sub naught. It's the equation of this line. The equation of that line is, so U equals,
All it is V minus U sub naught equals M minus M sub naught.
too
Or,
much-
sorry,
too much
M times V minus M.
true, but it's just too much thinking. Because my slopes are so nice, they're zeros and undefined spaces. Oh, by the way, you guys, this is a really, really, really small region. Like when I subdivide the smaller regions with the double intervals. I guess I can think of the areas being the, the area's gonna be delta U, delta V. All right, that's a really small rectangle. But what if I wanted to transform over to the XY coordinate plane? Maybe it's the case that when I transform over, it's not quite linear like that. Maybe it looks something like that. That being the case, maybe you should come in and see how I transformed those boundary points. For example, if I had some vector valued function R bar, you got U and V, represented as some function, I'm making these letters up as in your error, you guys. How about H? In terms of U and V. Plus, how about a K? You got a U and V. So those are two functions. Oh, did I forget my I bar and J bar? It's a vector valued function. But the functions H and K are continuous, or excuse me, real valued functions on both U and V. And I maintain that if I were to differentiate this vector valued function, all I'm really going to get is this. I'm simply going to get my H prime plus K prime. Because I can differentiate vector valued functions. Now, if I allowed myself to have this function that I called, is that H in U and V? If I give it a name, call it simple, call it X. And if I allow K to be, well, I'll just call it Y. Maybe I can see how I can commit to that transformation. Because I think over here, if this is what I consider over here and here, small changes in these directions, like how about a Y in an X? I think when it comes to these directions, maybe I can quantify them. Actually, I made a mistake, you guys. Those are direction vectors. Shoot. What I really wanted to do is look at the side of the sum, parallelogram. So I'll multiply by something. Here too, I'll multiply by something. And so I guess what I really have down here is delta x times some distance. And up here I've got my delta y times some distance. I'll call them r's and s's for a minute. That being the case, the area that parallelogram is, oh shoot, it's not a parallelogram, is it? Darn it. But you know what, if this region is small enough, I think I can consider the corresponding parallelogram's area to approximate the area that black patch. As long as delta x and delta y are small enough. It's just the way you and I compute the area of a parallelogram is with, anybody?
Gotta give us a second.
The writing business again.
No, it's crazy that we have to do this.
What was your question?
How can I compute the area of parallelogram?
Just two triangles.
Oh, true, true. Let's be more sophisticated.
Be more, yeah, that's what I just said, based on height.
Um,
No.
But there's probably.
but I thought this is a course in vector theory.
Obviously not.
So the trigonometry, what you do with vectors to compute the area of the parallelogram?
Cross product.
It is. So if I take a peek at the cross product, I think I get this. I get the cross product of two vectors, particularly those involving derivatives. How about this function x is partial with respect to u, and this function y is partial with respect to did I say with respect to u? Sorry, can I change that? I meant over here. This could be considered a partial of my x function with respect to those two variables. And that being the case, in the end, I can compute the area of that parallelogram just by evaluating the magnitude of a cross product, particularly the partial of these functions.
Sorry.
It's quite all right.
So it's just x cross y?
No, it's something cross something. I just haven't shown you what it is yet. But I'm going to look at the cross product of these two magnitudes. It's just that when I look at the cross product of those two magnitudes, I think I generate something like this. It's the magnitude of the cross product with this vector. Let's say the partial of x with respect to u, and the partial of x with respect to the other variable v. And then I'm going to look at the partial of y with respect to u, and the partial of y with respect to v. Oh shoot, I don't have the third components. Yeah, they're just all zeros. I'm looking at two space. It's just if I evaluate this determinant, you guys know what I'm going to get. I'm going to get the partial of x with respect to u times the partial of y with respect to v minus the partial of x with respect to v times the partial of y with respect to u. This becomes so important, I give it a name. I call it a Jacobian in terms of variables u and v. It's what allows me to commit to transformations from one space to another. It's sort of like our higher level thinking of our U sets. It's no different, it's just a higher dimensional space. So if I come up with an integral that's difficult to evaluate, then I can, if it makes it convenient, commit to this particular type of transformation. And you guys, let me throw a couple examples at you real quick. Oh, you guys, I don't remember what they are. I made some examples. Like, for example, how about this? Double integral over region. Here's what's in the integrand's position. And I'm integrating respect to area. Oh, by the way, that region R is described this way. It's simply connecting these places in a very linear fashion. Guys, I'm nervous. Can I take a peek at your textbook? Jeepers. Guys, I didn't do my homework.
Messed up?
No.
That never happened.
No, it does. I didn't do my homework and read your book before I came to class today. I just made up some examples off the top of my head, wrote them down. But it's now occurring to me when I'm looking at the homework set for this exercise set, the author doesn't do this. He tells you what the substitute's supposed to be.
He tells you what the what?
All the substitutions are supposed to be. And I'm not with my examples.
That's serious.
I want you, yeah, I know. I want you to be at this level. That's what. So now I'm panicking. maybe need to actually write some more exercises, post them as homework. I just don't know if I'll get to them today. So be aware of that.
We can also
We
just
just like,
not look at the subs.
yeah, look at it, do the example of that.
Yeah, you can hide them. Well, yeah, you can do that, you can do that.
But it's-
Sorry, I should have figured that out before class.
Would it be too hard to like make up ourselves the subs?
Look at those examples without substitution.
I don't think so. Matter of fact, with my examples, I'm not gonna give you the subs, we'll identify what they are. But you guys, look at this integral. Doesn't it look nasty? I mean, I got the product of a transcendental and a algebraic function, the integrand's position. I mean, I think it looks fairly complex. If I could do something like I did back in Math 30, maybe just massage it, give it a U sub, clean it up a little bit, then maybe I think it might be easier to evaluate. So you ready? Let's give it a shot. I think to commit this whole new technique I'm referring to as Jacobians, I'm gonna play this game. I'm going to allow U to be something, and V to be something else that cleans up what you see in the integrand's position. I think quite naturally in this example, I think U and V should be x minus y, and x plus y, or vice versa, the order doesn't matter. And what I want to do is dive in here and just change my integrand to look like an integral involving this. I think if I were to do that, actually it's a piece of cake, isn't it? I think the integral immediately becomes this. That's the integral of, is that a u squared? And then a cosine squared of v. And I'm going to integrate with respect to u and v. I don't know which one first. I'll make that decision later. So now, tackling the issue of identifying the bounds of integration, I should maybe draw a picture. Why are you guys so quiet?
What is,
Draw a picture.
Of the region R?
So you don't have to transfer the x.
Thank you. I think I'm 100% wrong. If this is going to be like a U sub, I think perhaps there's going to be a scale change along the way. That's where the Jacobian comes in. So to find out what the scale change is before I go to the region R, let's compute it. I think the Jacobian is simply going to be the evaluation of this 2 by 2 3 by 3 determinant. Gosh, what did that look like? It was a partial of x vector, and then the partial of,
X vector v,
and then the partial of.
y over u, well, partial, blah, blah, blah.
Oh, by the way, I did not look at the book. Some texts I look at have these two interchanged. Who cares? In the end, it's the same computation. And I think in this particular example, that merely ends up being I bar, J bar, K bar, couple of zeros, I've got to slow down. Actually, I don't know what these partials are. We'll partially differentiate with respect to x. What do we get? No, I think another mistake. Because I want to partially differentiate x with u. I can't. I'm like this. So I got to come in and apply my math D skills and solve for x and y. Instead of solving for x, I'm just gonna add these two equations together. Y is completely eliminated. Clearly, x is going to be nothing more than, how do u plus v over 2? Is that okay, Madeline? And I think likewise, subtracting, I don't know, maybe the second equation, or the first equation from the second, is that going to give me a v minus u over 2? I said v minus u. Over 2 being another name for y. Oh, you guys, piece of cake. Let's come in and evaluate. I think the partial of x vector u clearly is. I said clearly, but 1/2, I heard that. The partial of x vector v is going to be. You guys are killing me. Well, since you're on such a roll, just finish it up.
You gotta give us a second, we're still writing it down.
And I can evaluate. Is that going to give me, I can't do it. Yeah, it is 1/2, isn't it? Sorry, I'm slow. Are you there? If you are, then I guess I've got my scale changed. I'll fix my clumsy mistake. I guess I've got a factor of 1/2 now. I'm going to integrate respect to, I think, v, then u. I don't know yet because I don't know what the picture looks like. So let me draw a pretty picture. In drawing a pretty picture of that region R, can I get rid of this? Oh, maybe I can't. Hold it. I won't get rid of v yet. I said x is equal to u plus v over 2. Likewise, y is equal to v minus u over 2. Okay, now I'll give myself some room. Because I think in the xy quarter plane,
Is that a times?
it is a times yes. By the way, you guys, when I discuss theory, I know I started in UV plane. I transform over to the xy quarter plane. It's just that this time around I'm going backwards. So as long as that transformation is what we refer to as single valued in Math 33 language, 1 to 1 and on to, I can create an inverse transformation. So starting now in the xy quarter plane, let me plot those silly points that are 0, 1.
Is that B plus B, or is it B plus squiggly?
Well, you can call it squiggly, I guess. So
I think it's a
v,
U.
u plus v.
We forgive him a while ago.
Okay, V, R, square symbol, it's all the same, isn't it? And a point 1, comma 2.
Is
And-
there any verse?
What's that?
There aren't any verse?
Then 2, comma 1. And then 1, comma 0. Okay, so it's a diamond. So there's my region xy coordinate plane. Now let's see what it looks like in the corresponding UV coordinate plane. Here's the U axis. Here's the V axis. Actually, it's going to be a very linear type of transformation. I don't know, how do you think I should find the corresponding values? Anybody? Well, can't I do this? Can't I pick this up off the inkboard, slap it in for U? Pick this up, slap it in for B? Or would it just be easier in this example, because everything's linear, just to plug in the specific points?
I can only do that, it's just linear.
What's that?
You said because it's linear?
Yeah, because all the linearity relationships between the x, u, v, and the y, I think all I really need to do in this example is check the endpoints. Let's check them. If x is equal to, I'll label these, 0 and y is equal to 1, let's find the corresponding u and v values. Well, if x is 0 and y is 1, isn't u, v going to be negative 1, 1?
Could you write that down?
Yeah, all I'm saying is this. If x is equal to 0 and y is equal to positive 1, then I think the corresponding u and v values are going to be the following. Look at the first equation up there. U is equal to my x value minus my y value. And v is equal to, well, my x value plus my y value. I think it simply gives me the order pair, negative 1, 1. All right, you guys, let me start flying with my arithmetic. Now when I plug in the point 1, comma 2, using 1 and 2 for x and y respectively, does that give me a negative 1, comma 3? And then taking a peek at the point 2, comma 1. Well, here plugging 2 in for x, 1 in for y, doesn't that give me, is that a positive 1, comma 3? And then lastly, I guess that generates, what is the point I'm missing? Oh, here it is, 1, comma 0. Plugging 1 in for x, 0 for y respectively, that's going to generate a positive 1, comma 1. Okay, so I guess I'm just getting a nice nifty little rectangle.
Is there a reason for that?
Reason for what?
Like, is it just coincidentally nice and like proportional and stuff like that, or is that something that happens with
See, I think the proportionality is not important. This could be a stretch figure. So I think proportionality is not the issue. I just think that the issue is that there was a linear relationship among the quantities. I said x, y, and z, I meant x, y, u, and v. And, oh shoot, you guys, this is going to make my life a piece of cake. Actually, to integrate respect to v first, it's just a linear relationship. My extreme values for v are going to be 1 and 3 respectively. And my u values are ranging from negative 1 to positive 1. You guys, isn't this a piece of cake?
So, since you're subbing u and v into the surface equation, are you rotating the whole three-dimensional surface? Or are you just rotating the region that you're integrating?
Now, I gotta confess, I was only looking at the smaller region, but it does hold true for everywhere else in the plane. I think with this transformation right here, no matter what other geometric figure I had in the xy coordinate plane, it's gonna transform in a similar fashion. And like Madeline was pointing out, maybe there is a nice clean proportionality here, but jeepers, I don't know, if I threw in a 5 here and a 2 there, I think it's gonna give me a scale change on the way as well. Oh, by the way, is this healthy? Is that easy to integrate? I couldn't hear them.
Yes.
Oh yeah, piece of cake. To integrate respect to V first, you would. What's substitution?
1 plus cosine 2.
Thank you. Use your double angle identity. And by the way, after that, that is a piece of cake respect to U. Kathy?
I was wondering why you were saying that you could take the U and plug it back in down there, you just get an identity, so you can just read off that in the first place. You run it with x equals s, so it doesn't seem at all helpful. You plug the u's and v's back in.
Oh, you know what? That's true. But technically speaking, I wanted an equation correspondingly in terms of u's and v's. So what I could have done, let me change colors so you can see what I'm adding. Do you guys think you can immediately tell me what the equation this line is right here? Just this one portion. Anybody? You guys, y equals x minus 1? Ooh, that was a little scary. That being the case, to come up with a corresponding curve over here, the u to be coordinate plane, check this out. Let me take these pieces. I've got a u being equal to x minus 1. Here's another name for y. Well, at least on the line segment red. But this ends up being nothing more than, is that a
U equals 1.
positive 1? And if I take the second equation up there, my v, and replace y with, I've just lost it, my x minus 1. I think I get this.
This is how we do it if it wasn't a linear relationship.
Yeah, and I can simply identify what these curves really look like. Actually, look at this. If u is equal to 1, doesn't that simply give me this right here, line segment? And so I think it just transforms over here. If I get the equations as these boundaries put into this picture. What about a double integral like this? And you guys, I was merely trying to make up some examples where in the integrand position I do have issues in terms of integrating. What about a fraction like 2y plus x? And downstairs a y minus 2x.
Can we do these in 3 variables?
Absolutely.
We should.
And if I have a boundary, that region R with these endpoints. Sorry, you guys, I have to look. I don't want to mess it up. I don't want my numbers being too massive. How about negative 1, 0? Negative 2, 0. 0, 4. And 0, 2. You guys can erase. And if I were to sketch that region, in the xy coordinate plane,
Region on.
plotted the first point at negative 1, 0. Then negative 2, 0. And then 0, positive 4. And finally 0, positive 2. There's a region I generated. Now, I do think what you see in the integrand's position does cause me some problems in terms of the integration process. That looks like it's difficultly anti-differentiated. So here too, I think this double integral is a good candidate for a Jacobian transformation. That being the case, I will commit to the transformation. I will compute my Jacobian. I think my Jacobian is merely going to be the partial of x with respect to u times the partial of y with respect to v, minus the partial of x with respect to the other variable, times the partial of y with respect to its other variable. And I think in this particular example, this should be a piece of cake, because I've just got linear expressions. Does that give me, you guys, I really can't read that part. Is it positive 1 times positive 1? Is that okay? Oh, it's not okay. I'm sorry, I really couldn't see it. I thought it was solved for, I solved for x and y already. I didn't. I guess that truly is my mistake. Since I have haven't found what x and y in terms of u yet. I've got to
Well-
not differentiate yet.
Do we still wanna pick those values for u's and v's? We have 2's.
Oh, thank you. My goodness. What do you think I should allow you to be, u and v to be? I mean, just naturally.
What's the next?
Yeah, the top and the bottom. But you guys, in this particular example, I can't compute the Jacobian yet because I haven't solved for x and y in terms of u's and v's. So, let's use math B again. I think if I were to multiply the first equation by 2, add it to the second, wouldn't it tell me that 2u plus v is equal to, is that a 5y? Which means I think y can be interpreted as nothing more than 2u plus v all over 5. You guys might raise it too much. Now to solve for, or I shouldn't say solve, but to get rid of the variable x, so you guys tell me what to do. Multiply by -2, add it to the first. I think it's going to give you u minus 2v being equal to, is that a, I can't do it. So 5x. I'm a little slow today. That means x can be interpreted as this difference divided by 5. All right, you guys, now I'm ready. I'm ready to come over to my Jacobian. And I think the partial of x with respect to u is going to be nothing more than 1/5. Times the partial of y with respect to v, which is also 1/5. Minus the partial of x with respect to v. That would be, is that a negative 2/5? Times the partial of y with respect to u, which is going to be positive 2/5. Oh, come on, it can't be that nice. Jeepers, I'm sorry. Is that just simply 1/5? My apologies. So I guess to rewrite that integral, I'm going to have the following. Shoot, I'm still out of room. Man. No, I can't. I might need them. I'll write over here. So I think this becomes an integral in which my numerator becomes a u, denominator is a v. I'm integrating with respect to u and v, but I've got my scale changes, positive 1/5. What I need next is to find out what the corresponding image looks like in the uv coordinate plane when it comes to transforming this actual region in the sy coordinate plane. But you guys, here too, I think there's a nice clean linear relationship among all these variables.
Does the order in which we put the dv and du
No,
affect the Jacobian? Like the order?
Not whatsoever. It's completely independent. And I do think I ran a little too fast. I mean, I don't know if I really want to integrate respect to v first, but if I switch them, I'm just going to switch them. It'll just affect my Gaussian integration. Certainly, it's going to affect neither the function integrand's position or even the Jacobian as well.
What would affect the Jacobian?
These relationships. Simply how you assign u and v to represent expressions in x. Well, everybody, let's do it. I've got these special points. How about this one?